All right, hello and welcome. This is going to be one of the last lectures on the group theory. Depending on how I do on time, it's either going to be the last lecture or the second last lecture. So we are going to revisit something that you guys already know, at least hopefully. That is the special theory of relativity. So let's start off at the very beginning. So what are the postulates of STR? The postulates of STR are that the laws of physics are the same in all inertial frames, and the speed of light in vacuum is the same in all inertial frames. So let's do this. So postulates. Oops. Postulates of STR are number one, laws of physics are same in all inertial frames. And number two, speed of light is the same in all inertial frames. Okay, so this takes us to Lorentz transformations, and so you would remember that when we are looking at a transformation, uh, just in the xt plane, leaving yz as spectator directions, what we get is the following: x prime is gamma x minus v over c into ct. Actually, let me call this beta. Let's look a little better that way. Beta ct. Y primed is equal to y. Z primed is equal to z. And maybe I can make space for the whole thing in one line. And we have ct primed is equal to gamma ct minus beta x. So this has a nice sort of symmetrical way of trying to write it. Here, gamma, as you would remember, is 1 minus v squared over c squared whole to the minus half, and beta is v over c. So this, as we were saying, is something that is the transformation is only on the xt plane and leaves y and z as spectator directions. You can show that with the speed of light going to infinity, this reduces to usual non-relativistic physics to Galilean transformations. Very good. So now, again, this is something that is going to be familiar to you, but just to rejig your memory, what is the invariant interval here? So the invariant interval is the following. So this is given by delta S squared is equal to c squared delta t squared minus delta x squared. And it's very easy to see this. So suppose you are in a frame S prime moving with a velocity with respect to the x, along x with respect to another frame S. So in that case, you can start off with, delta S squared, and this is going to be, so what you do is you write this. So delta S squared is going to be what? Is going to be, as we have written, c squared delta t squared minus delta x squared. So this you can rewrite in terms of, uh, the primed coordinates as we wrote down above. And this is going to be gamma squared c delta t prime minus v, actually plus v delta x primed by c squared minus gamma squared into delta x prime squared by plus v delta x squared delta t. Sorry, there's no squared here. So you do this, and a couple of lines of very simple algebra. Just so this is gamma squared c squared minus v squared into delta t prime squared minus gamma squared into 1 minus v squared over c squared delta x prime squared, which is nothing but c squared delta t prime squared minus delta x prime squared. So you see that this actually stays invariant. This is something that you know well, but this is just to sort of reinforce the same ideas, if you wish. So this was something that I did with just one direction. But if you do it in all four directions, what is going to and if you do it infinitesimally, the line element, as it's called, is c squared dt squared minus dx squared minus dy squared minus dz squared. So this is what is kept invariant by these transformations. Okay. Now remember what used to happen for rotations. This is very reminiscent of rotations. What did we do there? So remember, the thing that was left invariant was s squared is x squared plus y squared plus z squared. We're speaking about 3 dimensions at the moment. So this was the thing that was left invariant. And it's very similar, okay? And again, as you would remember from your earlier explorations, what you can do is you can define something which is called a 4 vector. And like a vector that you can define here, you can define a 4 vector here, and except for x, y, z, we have this, also something like these, the first, or the zeroth component here is going to be ct. Okay. Now, in this language, we will call this x dot x, this x squared. This is going to be given by the transpose of the vector times some matrix eta into some other vector, the same vector here. So this is going to be, so this guy is going to be x mu. This is going to be eta mu nu. This is going to be x nu. Where this eta mu nu now, again, so this eta is going to be given by 1 minus 1 minus 1 minus 1, and the rest of them are 0. So I mean diagonals. Okay. So then what you see is, from here, it's clear that if you look at x dot x, this is going to be given by c squared t squared minus uh, x squared minus y squared minus z squared. Okay. All right. So this is what is left invariant. Now Lorentz transformations is going to Lorentz transformations, again, very much like the rotations that we did last time. I mean, previously. This is what takes x to x primed, which is, we call this some lambda into x. Okay. So now what happens is x primed dot x primed is going to be x dot x. That's the invariance. So this is going to mean, so you can just plug in this into our formula that we had earlier, whereby we said that x dot x is uh, x transpose eta x. So if you do that, what you end up with is the following expression, that lambda transpose eta lambda is equal to eta. So this particular thing actually is going to define for you what a Lorentz transformation is. All right. So this defines a Lorentz transformation. Lorentz transformations. In a sort of notation that we were using previously, this is x prime mu going to x going to x prime mu, which is a lambda mu mu x nu, which essentially amounts to saying that lambda mu alpha eta alpha beta lambda nu beta is eta. Okay, so now look at the relation that I've boxed. Okay, if you look at this relation, and eta is what you have seen it. So it's eta is a diagonal matrix out here. So eta is of course a symmetric matrix, right? So so the left hand side of this equation, of this boxed equation, is symmetric. Therefore, the right hand side also has to be symmetric, right? So this equation, this is a matrix equation that is symmetric equation. Okay. So that means that this has so this gives you 10 separate equations. So let's just try to understand it again. What is happening is when you are going to be trying to understand what Lorentz transformations are. So Lorentz transformations will start off. So this is So let's just write this down. So lambda is a 4 cross 4 matrix. So this has 16 entries, 16 independent entries, or 16, let's say 16 entries. Lambda transpose eta lambda equal to eta. This is a matrix equation, which defines lambda this is a symmetric matrix equation. As I said, the reason why this is so is very easily seen because the right hand side is a symmetric matrix. Hence left hand side also has to be symmetric. Now, if that is so, so these are the equations that, constrain the form of, form of lambda. So this is a set. So this is a set of 10 constraining equations. Okay, so what are we left with? So this reduces, so these reduce, lambda to 16 minus 10 equal to 6 independent solutions. Okay. Now, so what you have is in 4 dimensions. So in 4 dimensions, Lorentz transformations have 6 independent solutions. Now remember the following, right? Remember the following, that if you are looking at what this does, and if you only are in the subspace of x, y, and z, then this is very simple. This is something that you guys have seen earlier. So this is just this part being left invariant, which is just rotations, right? This is just that. So if there is nothing being done with the time part of it, then these are just rotations. So a sort of way to say it is that rotations, of course, will form a subset of this. Okay, so the 6 guys that you have, these 6 independent solutions, these are going to form under 2 separate classes, and one of them is our well-known rotation solution. So solutions fall under 2 classes, and this is, one of them is the following. So this is lambda being, so the 0 component being just not playing a role, and here you have R. If you go back to the defining relation here, and if you plug this in, it is easy to see that what actually comes out of this is R transpose R equal to identity. And these are, as we expected, these are just R's are rotation matrices in 3D. so which is our well-known and loved SO3 rotations. The others are going to be, so the other three, uh, so this is class 1 if you wish. The others are Lorentz boosts, and these boosts are, so for example, if you're looking at boosts along x-axis, from the earlier thing, this is going to be given by the following, right? So this is going to be of a form like this. So lambda is equal to gamma minus gamma beta minus gamma beta gamma. And here you are going to get zeros. You're going to get zeros, and here you're going to get a 1. So these are 2 cross 2. I mean, 2 cross 2 matrices here. Okay. So similarly, you are going to get, boosts along x-axis. I mean, so this is a boost along the x-axis. You can similarly get one along the y-axis, and you can get a similar one along the z-axis. I mean, actually, it's so you can think of these boosts very similar to, to the rotations, where you are actually, rotating between the time direction and one spatial, spatial direction. You'll see that sort of is the right way to. I mean, that is one interesting way to think about these things. All right, so okay, so you will have a few exercises to do here, but so now what are we going to do? So we will move on, and we will speak a little bit about the Poincare algebra as well. But yeah, so that's next up. All right, so the defining relation of this Lorentz group was the following, right? So we saw that this was the way this was defined. So eta mu lambda mu rho lambda mu tau is equal to eta rho tau. So this was the defining relationship of the Lorentz group. So so now what do we see? So what we know is determinant of product of matrices equals to product of its determinants. So that means the following. That means that, determinant of eta, determinant of lambda is equal to determinant of eta. So we see that determinant of lambda squared is equal to 1. So that essentially means that determinant of lambda can be plus minus 1. Again, so the other thing that we need to keep in mind is that, if we start off with eta 0, 0, then this is, so eta 0, 0 is going to be what? Eta 0, 0. I'm going to write the right hand side here first. So this is eta mu nu lambda mu 0 lambda mu 0. So this is going to be what? This is going to, so let's split this up. So this is going to be eta 0, 0. So, there's a sum over mu and nu, and the only things are having diagonal entries. So this is going to be lambda 0, 0 squared plus eta I into lambda I 0 squared, right? So eta 0, 0 is going to be 1, eta I is going to be -1, and let's do this. So this is going to be, so if we plug this in, then what is going to be happening is we are going to get an equation which is lambda 0, 0 squared minus lambda I 0 squared is equal to 1. Or lambda 0, 0 squared is equal to 1 plus lambda I 0 squared, which is of course greater than 1, greater than equal to 1. So if lambda 0, 0 squared is greater than equal to 1, so you can have lambda, so let's put this in blue, lambda 0, 0 is greater than 1, or lambda 0, 0 is less than equal to -1. So these are the two things that, so now, so what you have is the following. So constraints, determinant of lambda equal to ±1, and lambda 0, 0 mod of that is greater than equal to 1, define 4 disconnected pieces, of the parameter space. Okay, so now there's going to be some nomenclature. So let me try and write this down. So nomenclature, if you wish. And here we go. So 1 is the full Lorentz group. This is just L belonging to which O13 with entries in the reals. So this would mean that lambda belongs to general linear 4x4 matrices with real entries subject to lambda transpose eta lambda equals to eta. So this is the whole group. Number 2, we have what is called the proper Lorentz transformations. So this is another very important definition. We're going to be calling this L plus, and this is going to be SO13, and again in ours, such that, so okay, lambda belongs to O13 and determinant of lambda is +1. Along with the proper, there is obviously the improper. So improper Lorentz transformations. Improper Lorentz transformations. We're going to call this, just bear with me for a second, where I make the necessary changes. So this is going to be L minus, and there's no SO stuff here. So this goes away. Maybe a bit better if I just, and so the determinant now is going to be given with a minus sign. So that is -1. Okay, so that's the improper. And then there is going to be something called the orthochronous Lorentz transformations and the non-orthochronous Lorentz transformations. Let's write those down. Orthochronous Lorentz transformations, that is given by a sign which is upstairs. So L with an upward arrow. This means that your, again, lambda is going to stay in, is going to belong to 013. That is fine. And now your determinant, so lambda naught naught is going to be greater than +1. And of course, as you can well understand, there is going to be something which is called the non-orthochronous make the necessary changes. So non-orthochronous is L with a downward arrow now. And there, as we discussed, this is the other part of the group. So L is going to, lambda naught naught is going to be less than equal to -1. Okay. We are going to be mostly interested in something which is the restricted Lorentz group. So this is going to be, so this is what we'll be mostly interested in, L plus with an arrow upstairs. So this is going to be the intersection of the L upstairs with the L plus. So this is thus going to be all of these lambdas that belong to O13, just to make sure that we remember that these have real entries. And the determinant of this is going to be equal to 1. And the lambda naught naught is going to be greater than +1. Okay. So this is the group that we are going to be interested in. And this is what we are going to work with. Okay. All right. Now, what do we want to do? What we want to do next is we want to find out the generators of the Lorentz group, and we want to figure out what the algebra looks like And that is going to form the last lecture. So I've given you an idea of what the Lorentz group is. This is probably something all of you are familiar with, but yeah, so that's that. And in the next lecture coming up very shortly, we will try to work out the details of the Lorentz algebra. And so, we find out what the form of the generators are, and then we shall try to write down the algebra, and we will give you an idea of how to classify the irreducible representations. I should warn you that this actually, trying to understand the representations of the Lorentz or the Poincare group is actually a very is a lot of work. So we shall not actually be doing all of that work. But of course, I can point you to places where you would be able to get more details of it. And, hopefully as you go ahead, you'd learn them in even more details. But at least an idea of what you can do would be nice. So yes, so that's it for the moment. And we will see each other shortly again. Well, at least I'll record things very shortly. All right, then. So this brings us to the end of the first lecture on uh, the Lorentz group, and there will be one more. All right. Bye bye.